I'm going to do another video here on using, maybe I haven't made a video back to back, but I've made videos on using a coupler to do antenna measurements and a return loss bridge to do measurements. But I don't think I've done them at the same time. And I know it's a very, very confusing subject. It's also a subject I believe everybody wants to do. It's like everybody who has a spectrum analyzer wants to do a return loss measurement. Now, if you have a nano VNA, you certainly can do it there, and it's probably a better tool for this. But a lot of people want to do it with their spectrum analyzer. And so let me show you how to do it. So I'm going to use two things. I'm going to use a coupler. This one's good from 10 to 100,000 megahertz. And I'm going to do it with the return loss bridge. This is one of those cheap Chinese ones. And so you're going to need two things. You're going to need a spectrum analyzer. Okay, so I'm going to be using, where's my spectrum analyzer? I'm going to be using this. And then you also need a generator, okay? And you need one of these. Now, if you have a tracking generator, you're halfway there, okay? But I'm going to assume you don't have a tracking generator and do it a harder way. And so I have a little standalone generator here. I've shown a video on this before. And I have it set up to output a sweep. And it's sweeping between 100 megahertz and 200 megahertz. Okay, so that's what we see over here. The sweep is going from 100 to 200. The spectrum analyzer is set up from 100 to 200. And you can see that it's nice and flat as it goes across. Okay, so all spectrum analyzers have a hold function. Okay, so I'm going to do trace max hold. And so if you have a tracking generator, you don't have to worry about things like this. But it's recording all of the peaks. And it's going to give you some little dropouts because because it's not tracking. You're kind of asynchronous, and sometimes you get some funniness now. Well, you can see I've set it up so that that line right there is a particular condition, and that the sweep generator is nice and flat. So we're just showing that, you know, you could measure this and do a subtraction and a normalization and all those other things. That's just too confusing for this purposes of this video. It's better if you do that, but for this video, I just want to get the basic concept out of the way. And that is that we have a tracking generator, a non-tracking generator, but we have a pretty linear response here from 100 megahertz to 200 megahertz. So there's really no reason to calibrate, okay? And so we have this sweepy thing going on here. All right. So the next major idea that we have to get is what are we measuring? Well, we're measuring return loss. What does that mean? That means that if you had a 50 ohm load, then that tracking generator would go into that 50 ohm load and nothing would get reflected. There'd be no power left over. It would all get absorbed, okay? And so right now I have the bridge set up where it's open. And remember on your nano VNA, sometimes you have an open and a short and a load. Well, we have an open condition. An open condition means that the RF comes there and it says, whoops, better go back. So 100% of the signal goes back, and 100% of the signal goes to the spectrum analyzer. And so that's going to be its maximum value. So that line right there, that's as much as it can get. Now, if you have a good antenna, then it'll drop down. If you have a perfect antenna, hopefully it'll drop down a lot, right? So let's put in a perfect antenna, okay? I happen to have a perfect antenna, and it's right here. It's a dummy load, right? Remember the VNA? Yeah, opens and shorts and loads. Well, here's the perfect load. Okay, so we're going to put the load in, okay? So we've just added a 50 ohm load, which means that all of the signal is being absorbed and there's none reflected. And look at that, very little reflected, okay? If we do that max hold thing again, you can see that we have a line way down at the bottom. So that's the very best return loss, right? That's like an SWR of 1.00001, right? It's really, really good. I have this set up for 5 dB per division. So it's actually 5, 10, 15, 20, 25. So that's at 25 dB. So that's as good as we can measure. A perfect antenna will measure minus 25 dB return loss. In this particular setup, it's a function of how good your bridge is, okay? But a perfect antenna will look like this. So let's turn off that. Okay, that's a perfect antenna. Now let's put on a real antenna, okay? So I'm going to put on a 2-meter J-pole. And so we should get a dip around 144 megahertz, right? And so we can watch it, all right? So remember, we're sweeping between 100 megahertz and 200, so we can watch it go. And then, whoa, it just dipped right there, whoa, and then it came back up, okay? So we're gonna do that max hold thing. And there we get a dip. And we're gonna have to let it run a couple times to get rid of all of those crunchy bits. Okay, that's pretty good though. So there's where our antenna is at the very best, right? It would be a perfectly bad antenna if it was at this line here. And it'd be perfectly good antenna if it was down here. But it's up here somewhere. So where's that dip? That dip's at about 5, 10, 15 dB. Well, that's pretty good. 15 dB is probably about an SWR, maybe 1.2, something like that. You need to get a chart, right, that converts dBs into SWR. But for this video, we're just going to call it SWR. If you're at 10, I think that's an SWR of, I'm gonna quote it wrong now. 20 dB, I know 20 dB is 1.2, okay? So 20 dB is 1.2 to 1. So we're really good right there. So we can take our marker over. Where's that? That is here at 147.3. So the antenna is good from about 143.5 to 149. So definitely the whole 2 meters like right in here, right? So that antenna is tuned really well right there. It should be, I tuned it. But yeah, right in there is our antenna, okay? And we can zoom in and stuff like that. But what I want to do is I want to remember this one, okay? And so I'm going to, that's the A trace. And I'm going to put the A trace in C, right? This says A, B, and C. If we go back, we can turn off A, and we can turn on C. So there's C. So we're going to remember C, right? All right, so we have C. So let's just remember we have it, and we'll get rid of it for now. And we'll go back to A. Okay, so that's how you do it with a bridge. So let's go and do it with a coupler. Now couplers are kind of strange. They say input and output, but we're going to use it backwards. Anything that returns here goes this way. So it's a one-way valve. This goes through here. This does not go through here, right? So if we input here and we have a load over here, nothing will get reflected back. And if our load is wrong, we will get a reflection back. So we're going to put our function, our RF generator into the out, and we're going to put our antenna on the in. I know it's backwards. So tracking generator comes in here, the antenna goes here, and the spectrum analyzer goes on the coupled port, okay? So let me do that. I'm going to put my spectrum analyzer there, and I'm going to take my generator. I'm going to put it into the out. I turn this upside down, it'll be easier. Okay. All right, so now we have an open, so we should get 100% reflection. So let's go back. And where's our 100% reflection going to happen? Guess what? Right at that line. So 100% is still 100%. It's a little bit lower maybe. Yeah, it's a tiny bit lower. So there's a little bit of loss into the coupler. Okay. So we could adjust for that. We could say it's amplitude. There we go. So I put it back. So we'll do a trace max hold. So I put the reference level at -16 instead of -15. So now our zero line is back exactly where it was originally, that line. So this means 100%, this means 100% reflection, okay? Okay. Now, let me put our perfect 50 ohm load on this setup. And now we're way down there, okay? So let's do a max hold on that. So now this is our perfect antenna. So it's 5, 10, 15, 20, 25, about 28. It actually is a little bit better dynamic range than the bridge. So this particular coupler is better than the bridge, okay? So a lot of people think that bridges are the best, but it's been my experience I get better results with the coupler. So I'm just going to use couplers usually. Okay, so that's what a perfect dummy load does. And so let's put on our 2-meter J-pole and measure it. So I'm going to add the 2-meter J-pole, and we should get a dip there in the middle. And so let's go do the max hold thing. Let's do one more sweep. Let's see if we can get rid of that little bit right there. Yeah, that's good. Okay, so let's do a store on this. So we're looking at that. So now what's the antenna measuring? Well, it's 5, 10, 15, about 17 dB down. Let's compare that with our stored one. Remember, in C that we have the bridge. So I'm going to turn that back on. And there it is. Look at that. They overlay each other perfectly. Okay, I'll C is on. Now I'll turn off A. Turn off A, turn on A. So you can see it doesn't matter which one we used. No, we got the same result. All right. So I hope that helps. I know it's a confusing issue. I know you'll have to do this a couple times for yourself in order to get it right. The real tricky parts are using the coupler backwards. That's a weird thing. That took me a while to figure that one out. It just doesn't seem right. Because why else would they label it input-output? I mean, really, why would you do that? The reason they're labeled input and output is one of the uses for couplers is to measure how much you're inputting to a device. So let's say you have an amplifier over here, and you kind of want to do leveling. You kind of want to make sure that you're inputting the right amounts of stuff. So you sneak a little bit off. It's like an RF tap. You're taking a little bit of the input and stealing it out to measure it, and then the rest goes through. But we want to use it backwards. We're going to come in, and then if anything reflects, it goes up. So that's the coupler. The bridge, you have to figure out how to hook it up. It's going to be sometimes labeled and sometimes not labeled. This one didn't come labeled at all, and very little instructions. So sometimes you have to figure it out. But I think all this one had was a dot on it. I think it didn't have anything else. It just had a dot. And if you looked at the literature, you could kind of figure out that's the in. So you want your in here, and then the spectrum analyzer hooks to the out. It's very different. It's very different from this. So if you learn this, then you'll be confused on this, and if you learn this, you'll be confused on this. So they're completely separate. On this one, you go in the out, and then you go out the in, and you hook up the spectrum analyzer to the forward coupled. On this, this one was labeled in and out and device under test, I think, DUT or something like that. Sometimes they're labeled DET, detector. Some detector should actually be over here. So they're going to be labeled all kinds of crazy ways. So bridges are confusing, but basically you want to have it so that things go through the bridge, and then if there's any mismatch, it comes out the other part. The mismatch comes out one side, right? And in this particular one, you go in, you come out, and then if there's any mismatch, it comes out this side. So it's these are very, very confusing. They're pretty cheap though. I'm not sure what the frequency range of this one is. I don't think it will go up as high as this one. It might. It might. I mean, gigahertz isn't all that high, but this one is made for a good range. So this one's made by Merrimack. I'm sure this is a discontinued model. It's a CRM-20-500. So -500 probably means it was only spec'd to 500 megahertz originally, but I've swept it out and it seems to work to a gigahertz just fine. And 20 might mean that there's a 20 dB loss in the coupling, something like that. So anyway, I might have confused you more than helped you, but that's the way it is. It is a confusing subject, and the big takeaway is it doesn't really matter if you use that one or that one, you're going to get the same result. And these seem to be a little bit easier to understand than bridges.